Hello and welcome to the first lesson for Study Unit 4. If you've reached this far, you should know that Unit 4 is really targeted at grades 6 to 9 of the new GCSE Maths course. So all of the topics in Unit 4 are the topics that are only assessed on the higher tier exams. Now, if you're doing higher tier, roughly half, maybe a bit less than half of the questions will be aimed at grades 4 and 5, which are covered in our study units 2 and 3. So if you want a grade 6, 7, 8 or even 9, then you'll need to really have a good knowledge of these study unit 4 topics. If you're only going to sit your exam at foundation tier, you don't need to study this unless you want to. So today we're going to cover two slightly different things, but they are kind of connected, and that is recurring decimals, specifically how to convert a recurring decimal into a fraction, and we use an algebraic method. And also we'll go back to bounds. We've done upper and lower bounds before, looking at intervals for upper and lower bounds. But at higher tier, you will need to apply this to calculation. So when you've got more than one number in a calculation, usually things involving measurements, and then you need to work out the upper or lower bound of the result of that calculation. So Iman, your target is a grade 7, fantastic. Grade 7 is roughly equivalent to an old GCSE grade A. So 7 is a good target, and I think to get a grade 7 in the new exams, you'll be aiming for about 50 and between 50 and 60%, I would say roughly, on the new higher tier exams. So a good target. Probably only about 2 or 3% of the whole exam cohort will get a grade 9. That's your target, fantastic, but it will be tricky to get that top grade. Daniela, bounds, we covered it. I'll give you a link in a moment. So all I mean is that we covered upper and lower bounds in a previous lesson. You might have heard it being called error intervals or something like that. It's not too complicated, and I will recap on the work which I did previously in this lesson. So don't worry too much if you haven't worked with upper and lower bounds before. You might have just known it by a different name. So do make notes. As I said, some of the things that I'm covering today I've talked about previously, so I'm just going to push it forwards onto those people that are looking for those higher grades. It will be helpful to have a calculator. I've got mine with me today, and I'll show you, if you've got one of these Casio calculators, how to work with recurring decimals on here. I think I might have shown you briefly before, but we'll use the calculator for checking, but really the method that we use for converting a recurring decimal to a fraction is an algebraic method. You shouldn't need to use a calculator at all. Okay then, so if you're working through your ICSLM course notes, you will need to do the Unit 3 test paper before you unlock your Unit 4 materials. And the topics that we're doing today are covered in the first section of Study Unit 4. So we have Section 1, decimals and place value, recurring decimals, limits of accuracy. So you've got more practice questions in those sections there. You also have the textbooks, and from now on in these Unit 4 lessons, I'll only be referring to the higher tier textbook. So for recurring decimals, you will want to go back to Chapter 7. You've probably already done some work on Chapter 7 before, but if you go to the very end of Chapter 7, there's a section in there, Section 3, which isn't in the foundation tier book, converting recurring decimals to exact fractions is called. I left out the word exact because I couldn't fit it in. If you've got the book, fantastic. So it's the end of Chapter 7, and then for our limits of accuracy, it's Section 3 in Chapter 9. So I'll just put that in there. So a lot of this work that we'll be doing Study Unit 4 is kind of plugging the gaps. It's covering the things which I left out previously because they're only assessed at higher tier. So we'll be revisiting a lot of the things we've done, especially in Unit 3, and then building on them. So some of my lessons, because I'm trying to fit them all into 1 hour, might be a little bit bitty. So I'm really covering two separate things here, but they're kind of related, and you'll see why in a moment. So an overview of what I'm going to be covering this lesson. Now, types of number, you don't need to be worried about learning these. It's just to show you how it fits into context. So I'm going to talk about terminating recurring decimals, and then we'll look at these error intervals and see what that's all about. So as you know already, here's a summary. types of number that you'll be working with at GCSE level are whole numbers, which are usually called integers, and integers include whole numbers which are either positive or negative or zero. So this word might appear in a question, and you should know that it only means whole numbers. For example, you might be given an inequality, for example, a between -1 and +5, and be told to write down all of the set of all of the integers in that interval. So integers are only whole numbers. And then we have what's known as a rational number. And a rational number is any number that can be written as a fraction, one number over another number. And this includes probably most numbers that you've come across. Integers are a type of rational number. Any fraction, of course, a fraction or so a fraction that could be written one number over another number. And any terminating or recurring decimal can also be written as a rational number. By definition, a rational number is one number over another number. And then we have something called irrational numbers. We're not dealing with any irrational numbers today, but next lesson we will be. So if you tune in tomorrow, we'll be doing thirds, and thirds are square roots, which are a type of irrational number. Other irrational numbers that you might have come across when you were working with trigonometry, or the number pi is an irrational number. And irrational, as opposed to rational, means it can't be written as one number over another number. They can't ever be written using digits. Often in a question you might be asked to write a number as an exact value, in which case you would write it exactly as a square root or as using the symbol pi and so on. But they're irrational numbers, they can't be written using digits. Okay, so it's a good idea to have an idea of where all of these numbers fit in the scheme of things, especially when you go on and do more complex work involving proofs and so on at higher tier. So all fractions, one number over another number, can be converted to decimals by dividing the top number by the bottom number. That's really what we mean by fraction, is the top number divided by the bottom number. If you have a calculator, you can just do the division on your calculator, press equals, and it will tell you the decimal. If you're using one of these calculators, remember that you'll need to press the S to D button to convert it to decimal. If it's a recurring decimal, you press it again and it will change the form. If you don't have a calculator, then you'll have to use short division. This is something that we've done already, so have a look back at your notes and remind yourself how to convert a fraction to a decimal, either using short division or using your calculator. One more way might be to write it as an equivalent fraction over 10, 100 and 1,000, and then using place value. So that's how we convert a fraction to a decimal. Now, when we divide one number by another, there's only two things that are going to happen. Either we will get a terminating decimal, and there's a lot of definitions and talking here, but once we're over with this, we'll do some questions. So you're either going to get a terminating decimal, which has a fixed number of digits after the decimal point, or you're going to get a recurring decimal, which has got a repeating pattern in it. And these are both rational numbers, they're not irrational. So that's will always happen when you convert a fraction to a decimal. So terminating decimal, for example, supposing you had a fraction 33 over 100. 33 divided by 100, you can probably do that mentally. So what would that be as a decimal? So if you were to convert 33 over 100 into a decimal, 33 divided by 100 is quite straightforward. You just move the decimal point at the end 2 places. Perfect, yes. Mixed decimals, yes, you could have a number in front of it. That would be perfectly reasonable, because we're not saying, when we say A over B, the top number could be bigger than the bottom number. That would be an improper fraction. Any number that's not irrational can be written as one number over another, whether it's a whole number or a number less than 1. So if it's bigger than 1, A will be bigger than B, and if it's less than 1, then A will be smaller than B. Does that make sense? So we can define any number in maths using one number divided by another. And in history, before irrational numbers were discovered, it was believed that all numbers were rational, that you could always write them as one number divided by another number. Then they discovered irrational numbers, but we'll look at those in another lesson. So we've got 0.33, and there's just 2 digits after the decimal point and nothing else. So that's a terminating decimal. It stops after the second 3. And a recurring decimal, as we mentioned, has a repeating pattern of digits, and there can be 1,000,000 digits, and then there might be another million, and the pattern might repeat. It could be a very big repeating pattern, but it does repeat. Here's a very simple example, which you've definitely come across and you should know already. If you worked out 1 divided by 3, if you did it as short division, you would have 0. Do you know what the answer is? Yep, Michael, what you've written there is an example of a recurring decimal. If those 3's go on forever, that is a recurring decimal. So if it's got a repeating pattern at the end that goes on forever, that is a recurring decimal. Yes, so 1 divided by 3 is a recurring decimal, 0.33333, and the 3's go on forever. And I know you can't type it in the chat box, but we indicate that with a dot above the first 3, and it's just a shorthand. Occasionally you might see a bar to indicate the repeating part, but just a dot is fine. It's what we usually use here in the UK. So the dot above 3 means 0.3 recurring. And this number is different from this number. So if I rounded this to 2 decimal places, I would get 0.3, but sorry, to 2 decimals 0.33, but it's not the same. A third and 33 over 100 are different numbers, obviously. So one's terminating and one's recurring. Here's some examples of some terminating decimals. So that's decimals that have a fixed number of digits after the decimal point. So for example, 3/4, you should know this one. It's 0.75 because 3 divided by 4 is 0.75. If I did it as a short division, that's the answer that I would get. 13/20 is 0.65. These are just random ones, but I'm trying to get you to spot a pattern. 4/25 is 0.16. And here's another one that gives us a terminating decimal. 37 over 80 is 0.4625. And that's it. There's no more digits after the decimal point. If you want to try these on your calculator, you can. You just divide the top number by the bottom number, press equals, press S to D if you need to on your calculator, and it will give you these decimal numbers. And they're just fixed. They don't have any recurring part. Now the question I want to ask, you may or may not know it, is how do you know when you have a fraction whether you're going to get a terminating decimal or a recurring decimal? Does anyone know what you can do when you look at these fractions to predict that before you work it out? You may have come across this or not. For example, you know that any fraction that's got a 10 or 100 or 1,000 in the denominator is definitely going to be a terminating decimal, because it's just going to be a number of tenths, hundreds, tenths, thousands, and so on. You know that anything over 50 is going to be anything over 50 will be a terminating decimal, because I can just convert it to an equivalent fraction over 100. I've got 20. Now I know that 13 over 20, I can convert that to a fraction over 100 by multiplying the 20 by 5 and so on. So that's kind of how it works. Does anyone know what the pattern is? Now what we're going to look at to work out whether it could be a terminating or recurring decimal is we're going to look, that's not a very clear colour, let me do a red. We'll look at the number in the denominator. So looking at the number in the denominator, to convert it into a terminating decimal, it's going to have to convert into a fraction over 10, 100, 1,000, 10,000 and so on. And the way that we check when it's a prime, not prime because none of these numbers are prime numbers, 4, 20, 25 and 80 aren't prime numbers. If you don't know the answer, I'm just going to tell you, and you might have to have a think about it later on. But the way that we know is that if we look at the denominator of the fraction, it has to have prime factors which are 2 and 5 and no other number. 2 and 5, by the way, both divide into 10. So it's to do with our place value system. So it has to have prime factors that are either 2 or 5, or a combination of 2 and 5, but no other number to be a terminating decimal. That's not that many numbers, so most fractions will convert to recurring decimals. These examples here are of that type. So for example, 4 is 2 times 2, 2 squared. 20 is 2 squared times 5. Now you're not going to be examined on this, but because you're working towards hierarchy, I just want you to get a wider view of how these numbers work. If you had 25, oh sorry, that's a mistake, that should say 25. 25 is 5 times 5, so it's only got 5s in the prime factor form. And 80 is 5 times 5, so it's 80 is 2 times 2 times 2 times 2 times 5. But we know that 2 times 2 times 2 is 8, and then times 10, 2 times 5. Remember, ages ago, right at the start of the course, we looked at writing numbers as products of prime factors. It's something that's quite useful in math for looking at properties of numbers. So that's how we know. If you can write the number in the denominator as a product of prime factors only involving 2 and 5, it will give you a terminating decimal. Okay, let's look at recurring decimals there. They're much more interesting. Now, a recurring decimal, as we mentioned, has got this repeating pattern of digits. Even the example that Michael gave earlier, the 0.26, there's some random digits, and then 333 recurring sometimes, that there are some more digits in the front, but at the end of the decimal will always be recurring. So a few examples. We knew that 1/3 was 0.3 recurring, so 2/3 is just 0.6 recurring. If you want to try that on your calculator, just work out 2 divided by 3, or do it by short division as a little test to yourself. And we can write that as 0.6 with a dot above the 6. Here's some examples with more than one recurring digit. So this is a little bit like the one that Michael mentioned, where we've got 0.8 and then lots and lots of 3s going on forever. So the 3s recur forever, and we write that as 0.83 with a dot above the 3. It's just a single 3 repeating forever. Here's another example, 7/33, 7/33. I don't know if that's how you say that. And this one, if we do 7 divided by 33, we get 0.21212121. So this is a cycle of 2 digits. The 2 and the 1 repeat forever. So the way that we show that is we put a dot above the 2 and a dot above the 1, and that means that the 2-1 goes on forever. Perfect, Daniela, yes. So the 2-1 goes on forever. And here's one more example, 8/37. 8 divided by 37, and that gives us 0.216216. I've chosen ones that have got very short patterns so that we can see it quite easily. Now this has got a pattern of 3 repeating digits. So how do you think? Where do we put the dots? How do we write this out? It's hard to type, but have a little think about it if you can. What we do is we write 0.216. Perfect, Richard. We put the dot on the 2 and on the 6 like this. Some have bigger repeating patterns. So a commonly one that you'll come across quite a lot is 1/7. So if you divide 1 by 7, 1 divided by 7, I'll do that on my calculator now. 1 divided by 7. In fact, my calculator here even puts the dots in the right place. We get 0.142857, and then that repeats 142857, 142857. So I don't know if you can see that if I put it up against the webcam, but the dot is above the first 4 and the last 7. So that's how they work. And any fraction other than the ones that have prime factors of 2 and 5 only will give us these repeating patterns. Now, as we've seen, it's quite easy to convert a fraction into a decimal. We either divide using the calculator or short division. But if we're given a recurring decimal, how do we convert it back into a fraction without a calculator? You can use your calculator. There is a button that you can use. It's just above the x squared button if you've got this Casio calculator. So you can enter recurring decimals and convert them into fractions using the calculator. But in the exam, you won't be able to. You have to do this without a calculator. There's quite a nice trick, and I'll show you how to do it in just a moment. But first of all, one more thing. And one of the reasons I want to show you this is because we're going to be using this quite unusual decimal 0.9 recurring when we look at upper and lower bounds. So this is an interesting pattern for simple single-digit recurring numbers. We've got 1/9 is 0.1 recurring, 2/9 0.2 recurring. 3/9, which we know is 1/3, it cancels down to 1/3, is 0.3 recurring, and so on. So whenever we have a number of 9ths, we'll always get this repeating pattern like this. 6/9, which is the same as 2/3. 7/9 is 0.7 recurring. 8/9 is 0.8 recurring. Now here is a really unusual number. This is an example, and I don't know if there are any other examples, of a number that can be written in 2 different ways. What is unusual, do you think, about the number 0.9 recurring? So this is the number where we've got 0.999999999, where the numbers go on forever. The clue is in looking at this bit. See this number 9/9? What's another way of saying 9/9? Perfect, yes. So 9/9 is equal to 1. So if this is equal to 1, then 0.9 recurring is also equal to 1. Don't think about it too hard. It's just one of these weird, quirky things in math. If we continue this sequence, the number 0.9 recurring is another way of writing the number 1. Weird. Sometimes math does weird things. So there we go. If the 9s go on forever without repeating, if they went on for infinity, that number would be equal to 1. It's one of those strange things. Things that go on forever and things that involve infinity often do quite strange things in math. They behave unpredictably. So that's something to bear in mind when we go back later to do upper and lower bounds. It's a little bit like rounding off, but for every 9 you have, you can always add another 9. So if you keep adding another 9 forever, you will eventually just get 1. With each 9 you add, you're getting closer and closer and closer to 1 until you don't actually ever hit 1, but effectively they're equal. Okay, so that was an aside. It's not really connected to converting recurring decimals to fractions. So what's this method that I was mentioning before I went off on a tangent? So here we have a recurring decimal, 0.18 recurring, and we want to convert it into a fraction. It just says write your answer in its simplest form of a fraction. So how do we do that? So I'm going to give you a method. The first step will be to write this recurring decimal with lots and lots of 8s after it. So we write it in full. We don't divide it by 100, but it's similar. And what we normally do, because this is an algebraic method, we set this number equal to a letter. And I've used X, but it doesn't matter if you use X or N or whatever letter you like. So we're just going to define this as X. So X equals 0.1, and the 8s go on forever. Now what we're going to try and do is get rid of that recurring part. And the way that we do that is if we see that there is one digit that is repeating, we're going to multiply both sides of this equation, and it is equation because it's something equals something, by 10. So if there's one repeating digit, we multiply both sides by 10. If there are 2 repeating digits, we multiply both sides by 100. If there are 3 repeating digits, we multiply both sides by 1,000 and so on. You'll never be asked to convert more difficult numbers usually than 3 repeating digits. So let's see what happens. So we're going to multiply both sides by 10. So if X is 0.18888 going on forever, then 10X is 1.888888 going on forever. And what we do next is we subtract these two. And as we subtract them, the whole recurring bit cancels out, just disappears, becomes 0. And so we just got rid of the bit that recurs. So if I start off with the 10x, I'm just going to write it underneath to make it a little bit clearer what I'm doing. So if 10x's are these, and 1x is this, and we subtract the 10x, we subtract the 1x from the 10x, look what happens. So we've got, obviously 10x minus x is 9x. But then here we've got 1 subtract 0, which is 1. Then we've got 8 subtract 1, which is 7. Then we've got 8 subtract 8, 0. 8 subtract 8, 0. 8 subtract 8, 0. So the answer here is just 1.7. And all of the recurring part, because we shifted everything along 1, when we subtract them, then all of that repeated part just cancels out like that. Yeah, they're all just zeros on forever, so we don't even need to write them. We just need to write that 9x equals 1.7. So how can we find the value of x then? Why don't we start the other way around? I'm not quite sure what you're asking, Iman. So we need to take away the smaller one from the bigger one. So I wrote the x first, then I wrote the 10x, but I've just put it that way around, just so normally you put the bigger number on top and the smaller number underneath. That's why I've repeated it there. So now we've got an expression which says that 9x equals 1.7. It's just an equation. And to solve this equation, I divide both sides by 9. I just write it as a fraction. So x is equal to 1.7 over 9. This is not my final answer, although it kind of looks like a fraction. It's not really a fraction because in a proper fraction there should never be a decimal in either the numerator or the denominator. So what I would need to do next is multiply top and bottom by 10, just to get rid of that decimal point then and make it into a proper fraction, 17 over 90. Check whether you can cancel it down, but you can't. There's no number that divides into both 17 and 90, so that is my final answer. So the 0.18 recurring as a fraction is 17 over 90. If you would like to check that on your calculator, if you've got a Casio calculator like me, I didn't prepare a slide, but I'll just show you very quickly. You can press 0.1, then press Shift, don't know if you can see that here, Shift and X squared, and a little box with a dot above it will appear. And in that box with a dot above it, put the digit 8, then press the right arrow to come out of that, and we've got 0.18, and then press equals 17 over 90. So that's how we can check it on the calculator, but in the exam you will need to show this method and show all of the steps. Got it? Okay, let's do another example. So this time we've got 0.27 recurring. So how would this look if we wrote it out in full? Can't get the recurring dot. Not to worry, you don't need the calculator to use this method. It only works if you've got one of these Casio calculators and you press the Shift and then the X squared. So if you notice that the box above the X squared button, if you have this FX85GT Plus, has a square with a dot, and you would put the recurring part in the dot. In this case, you would do 0. Shift X squared, if you've got that on your calculator there, and then in the box you would write 27, that's the repeating part. Then you would press the right arrow to come out of the box, and then you would press equals. Yeah, so if you've got that on my calculator, so I'm just going to see what the answer is on the calculator first, so I'm putting in 0. Shift X squared, 27 in the box, press the right arrow to come out of that, then equals. I've got 3/11. But you can't use this in the exam, you've got to use the proper method. So the first step will be to set this number to a letter. I'm going to use X again, because X, easy to use X, and write the number in full. So 0.27272727. Now remember, the object is to cancel out the repeating part so that we're just left with a fraction. There's 2 digits in the repeating part, so what are we going to multiply both sides by to shift the whole of this decimal along 2 places? Michael, are you putting down the answer? Yes, Richard, that was the number I was looking for. Multiply both sides by 100. I think, Michael, that might be the answer, but let's just see how this works out. Let's see if you're right. Now, with a simple one like this, you could write it. I think it's actually 27 over 99, but it doesn't always work, so you need to use this algebraic method. So we multiply both sides by 100. So 100x is equal to 27.27272727. Then the next step is to subtract those 2 numbers. So we're going to subtract x from 100x, so we'll just write it underneath. 100x, take away x is 99x. And then 27 minus 0 is 27, and the rest of the 272727, they all cancel out. So 27.27 recurring, take away 0.27 recurring is just 27. Okay, and the last step will be to just divide both sides by 99. So x equals 27 over 99. And then we need to check whether we can cancel that down. And we can see clearly that both of these numbers are multiples of 3. So if we divide top and bottom by 3. And the reason I'm multiplying both sides by 100 is because there are 2 digits in the repeating part. So I need to move everything along 2. So remember, when you multiply by 10, you move all the digits, the decimal goes the other way, you move all the digits along 1. If you multiply by 100, you move all the digits along 2. If you multiply by 1,000, you move all the digits along 3. So that way, if you imagine a place value grid in the background, we're displacing all the digits by that number of places, so that then when you multiply out, the recurring bit that we want will just cancel out. Does that make sense? Okay, so 27 over 99, I could divide top and bottom by 3. That would give me 9 over 33, though, and then I divide by 9. Actually, I should have known. They're actually both divisible by 9, aren't they? So 27 divided by 9 is 3, and 99 divided by 9 is 11. That's the number I got on my calculator earlier. So there we go, 3/11. Okay, got that? Happy with it? There we go. So 0.27 recurring is 3/11. Now I'm just going to end this bit of the lesson with an exam style question. So this is actually from the new 91 specimen set 2 papers. This is the 3H paper, so it's a calculator paper. So although you have a calculator, it does use this language. It says prove algebraically that the recurring decimal 0.3181818, going on forever, could be written as 7/22. So you can't use your calculator to help you with this. If you put that into your calculator, you just get 7/22. You need to use the algebraic method, which I just showed you, to convert this fraction. So it's very specific. If you would like to download a copy of this exam paper, here is a link to all of the Set 2 specimen papers written for the EdXL GCSE 9-1 exams. And there's actually 6 papers in there with the corresponding mark schemes. There's the 3 foundation tier papers and the 3 higher tier papers. And if you want to download written solutions, you can download them there. I've got written solutions to some of these papers. If you click that, you can see the written solutions there. So it's a good idea if you're doing your exam in the next few months to start practicing these past papers. So what do we do? Exact same method. First of all, we set the recurring decimal to x. We write it in full, so it's always the same steps. 0.31818. Sorry, yeah, 18181818. It sounds like that annoying phone number advert. And then we have got 2 digits in the repeating part. Daniela, you're doing exams in May, so you really need to start working through these past papers to practice. So multiply both sides of this by 100, because we've got 2 digits in the decimal, in the recurring part, and 100 has got 2 zeros in it. That's the way to remember. 1 digit, multiply by 10. 2 digits, multiply by 100. 3 repeating digits, multiply by 1,000, and that will get rid of the repeating part. And then we want to subtract. So we've got 100x. We're going to take away x. Just write it underneath if it helps, and take them away. So if I was subtracting these, 3 take away 0 is 3. Whoops. 1.8 take away 3 is 5. 1 take away 1 is 0. 8 take away 8 is 0. 1 take away 1 is 0. And so that those zeros go on forever. So we've just got 31.5. So when we subtract those, we get that 99x equals 31.5. And so to convert this into a fraction, we divide both sides by 99. So x equals 31.5 over 99. You could include a step where you multiply top and bottom by 10, so you would have 315 over 990. And then you would need to cancel down. But you know, because it's given to you in the question, we're actually almost there. All we need to say now is that 31.5 over 99. Check it on your calculator. Work out 31.5 divided by 99, and you should see that that is equal to 7 over 22. And that's our proof. So all of these steps here using the algebra proves that this recurring decimal can be written as this fraction. Okay. Lots of practice questions in your textbook, so try those, and most of the sets of past exam papers will have an example of this. Just having a quick look at the time, let's have a look at these bounds. Now, Danielle, I know you're saying you haven't done this before. This is a repeat of what we did previously. So if you want to go back and look at the lesson where I first introduced upper and lower limits and bounds, oh, I don't have a link. I don't have a link here. Not to worry, it's in a, I can't remember the name, I've sent it out this morning, I can't remember which lesson it was. It was one that I did on rounding and approximation in Unit 2, but I don't have a link to the actual lesson. So for foundation tier, if you're doing foundation tier, you do need to know how to write the limits of accuracy as an inequality, but for foundation tier, we're going to take this a step further and we're going to see how it applies to calculations. Now I'm just going to whiz through these slides because they are just copied and pasted from the last time we covered this, so this is just a quick reminder. So whenever we round a number, and this almost always applies to measurement values, so supposing I measured something when I measure something, the number that I write down is always a rounded number because it depends on what we call the degree of accuracy. If I'm measuring something in centimeters, that's quite accurate, but I could also measure it in millimeters. I can measure it in micrometers. I could ever get closer and closer and closer. So when I'm measuring something, because a measurement is on a continuous scale, I could write it to any given degree of accuracy. And when we round a number, then there's always a highest possible value that it could be before I round down, and the lowest possible value it could be before I would round up to that number. So it's not the exact number. There's this idea of an error interval either side. Upper bound and lower bound is what we normally call it. So the lower bound is the smallest that number could possibly be before I round it, and the upper bound is the highest possible value that it could be before I round it. So for example, if you've got a pencil that's 9 centimeters rounded to the nearest centimeter, the upper and lower bound for the measurement, if you want to type it in, you can have a think about it. So the upper bound, so I don't know, can't remember which way around I answered this. The smallest that this pencil could be is 8.5. Because if it was any less than 8.5, I would round it down to 8. And the biggest that it could be is 9.4999999 recurring, because if it was any more than that, I would round it up. So the lower bound is quite easy, 8.5. The upper bound is 9.4999999 recurring, as close as possible to 9.5 without actually touching 9.5, because by convention, if it's 9.5, we round up to 10. But this is where things get a little bit, don't think about it too hard. Remember that when we see 9s recurring forever, this number, 9.49 recurring, is actually equal to 9.5. So that's our upper bound. That's the number that we take for our upper bound. Don't think about it too hard. It's not really so difficult. Now, no, in real terms, if it was exactly 9.5, we'd round up. But the upper bound is always half of the amount that we're rounding to above, and then you take half below. So it's quite easy to work out once you get your head around it, and don't worry about it too much, because this is kind of the same. When we write it using inequality symbols, it will be a little bit clearer. So always go half the rounded unit above and below. Here's a couple of examples. So we've got 3 meters to the nearest meter, 7.4 to 1 decimal place, 562,000 to the nearest thousand, and 395 pounds to the nearest £5. So what's the biggest and the lowest value that these could be? Now, these are the same examples that hopefully you wrote down and you learnt about when we did rounding and approximation at the start of Unit 2, so I'll just go through them very quickly. So what we do is we say, okay, 3 meters rounded to the nearest meter, half a meter above and half a meter below. So the upper bound, so we go 0.5 above and below. So the upper bound, the highest it can be is 3.5, and the lowest it can be 2.5. 7.4 has been rounded to 1 decimal place, so if we've got 0.1, half of that is 0.05. So we go 0.05 above and 0.05 below. So the upper bound is 7.45, the lower bound 7.35. Okay, how about this one? You can type it into the box if you like. We've got 562,000, and that's been rounded to the nearest thousand. What's the biggest it could have been before we rounded, and what's the lowest it could have been before we rounded? Normally, we don't round whole numbers in this context. Usually it's decimal things, but just humour me for this one. So we go 500 above and 500 below. So we've got 562,500, and then 500 below that is perfect, John Paul. 561,500, that goes underneath. And what would be the range of values for the last one? So this is a bit different because we're rounding to the nearest 5. So the first thing you need to do is half of £5 is £2.50. So we'll go £2.50 above and £2.50 below. So that will give us the biggest possible value. I mean, actually, you would round up to the next £5 with this one. So it's not a great example, but it's just to give you an idea. So 397.50. £397.50, and yes, good, I'm just looking, Daniela, that's right. Oh no, sorry, yes, 392.50. You put 393.50, you took away 150 instead of taking away 250, but nearly. Okay, now we can write these error intervals as inequalities, and this is kind of a grade 5 kind of topic that might appear in Foundation Tier. So we can write out the range of values that A could have. So if A was the 3 meters to the nearest meter, A can be anywhere between, and we use these inequality symbols. And remember, this means that A is greater than or equal to 2.5, greater than or equal to. We're reading it the other way. So although we're saying that 2.5 meters is less than or equal to A, really we're saying that A is greater than, reading it the other way, 2.5 meters. And this is the typical way of writing a number is between two other values, so a combined inequality. And it can be equal to 2.5 meters, so it's always using this notice the little equal bit underneath. And it's anything up to, but not including 3.5 meters. So we don't have the little equal bit here. It's just strictly less than 3.5 meters. And we can write all of these in the same way to say that the value lies between the two others. So if B was 7.4 to 1 decimal place, then B can lie between 7.35 and 7.45. We've met intervals like this when we did statistics and we looked at class intervals, but we need to know in the context of error intervals as well. This is called an interval. Just a range of numbers. Okay, so we'll write them down. We can write all of these like this. Okay, just looking at the time. Here's the exciting bit, which is the sort of thing that you might be asked towards the second half of a higher tier exam. So when a calculation involves rounded numbers, and actually any calculation that involves measurements, so the volume of a sphere or the rate of flow of some liquid into a container, any of those kind of calculations that involve measurements potentially could be put into the context of error limits, because engineers would use this all the time because there's always some error intervals in the measurements. So what we need to do when we're doing a calculation is we take all of the measurements. We might want to find the lowest possible value of the final number, the highest possible value of the final number. So we're going to combine all of the upper and lower bounds for all of the numbers in different ways. So let's have a look at how this works. So for example, if you have a rectangular floor space and it measures 4.5 meters, 4.5 meters by 3.2 meters to 1 decimal place, it's been rounded, 1 decimal place. So in the context of meters, that's to the nearest 10 centimeters. So it could be, we could be very, very accurate and measure it to millimeters, but we've just rounded to 1 decimal place. Find the upper and lower bounds for the area of the floor. So how does that work? So the first thing we need to do is we need to work out the upper and lower values for 4.5, the length, and the upper and lower values of 3.2, the width, and then we combine those. So to find out the smallest possible value, we're going to multiply the smallest possible values of the length and width. And to find the biggest possible value, we multiply the biggest possible values of the length and width. So we kind of combine the error intervals in that way. So if we want to find the upper bound for the area, we would need to multiply 4.55, which is the biggest possible value for the 4.5, rounding it to 1 decimal place. Remember, we go half a decimal place either way. So we multiply those two together, and that gives us the biggest possible area that it could be. So if they were both took on their biggest possible values and we multiplied them, that would give us the upper bound for the area. How about the lower bound for the area? Can you tell me which two numbers I would multiply together to get the lower bound for the area? So take a quick drink while you're thinking about that. 4.45 and 3.15. Good. Sounds good to me. Perfect. Yep. Daniela and John Paul. That's right. So the lowest possible value for the 4.5 measurement will be 4.45. And then the smallest, did I say smallest? The smallest possible value. And then the smallest possible value, the lower bound of 3.2 is 3.15. We multiply them together. And that gives us the lower bound for the area. Pretty easy. Pretty easy, huh? It's quite easy when we're adding and multiplying numbers, but when we're subtracting or dividing numbers, we need to be a lot more careful. Have a think about why that is, because if we're trying to get the biggest number possible and we're dividing one number by another number, the number on the bottom needs to be the smallest possible, and the number on the top needs to be the biggest possible to get the biggest possible result. So it works in a slightly different way. And so similarly with subtracting, if you want the biggest number possible, you need to take the biggest number possible first and subtract the smallest number possible second. So you need the upper bound take away the lower bound of the measurement to get the smallest possible value. But I'll show you a summary in a second. We'll have a look at how it works. So here we've got a problem which is going to involve a division. So a car travels at 580 meters to the nearest meter in 15 seconds to the nearest second. What are the upper and lower bounds of the average speed of the car to 2 decimal places? You'll have to remember your speed, distance, time calculations. If you don't, remember the D goes on top, D for distance, and then speed and time. So we've been given the distance travelled, and we've been given the time, 15 seconds, and we're trying to find the speed. So speed is distance divided by time. That makes sense because we've got meters, we've got seconds. Meters per second means distance divided by time. So what are the upper and lower bounds? So first of all, we'll write down our formula. Average speed is distance divided by time. Now, the upper bound for the average speed, what's the biggest possible value for the average speed? Now, we need to divide the biggest possible distance by the shortest possible time to get the biggest possible speed. Does that make sense? Say yes if it does. Because the smaller the number we divide by, the bigger the result. Does that make sense? This is why this is higher tier, because you have to think a little bit more carefully about it. I'm not getting any yeses from the people watching. You don't understand. So when you divide Iman by a big number, you're going to get a smaller result. So let's think of an example. If you had 10 and you divided by 5, you would get 2. But if you had 10 and you divided by 2, you would get 5. And if you had 10 and you divided by 1, you would get 10. So the smaller the number that you're dividing by, the bigger the result. So to get the biggest possible value, the upper bound, we need to take the biggest possible distance and divide it by the shortest possible time. Right, to get the fastest speed. Does that make sense? You have to have the highest speed. So if you go a long distance in a very short time, you have to go really, really fast. So the further you go in the less time, the faster you travel. Does that make sense? You got it? Okay. Similarly, if you want to look at the smallest possible speed, you're going to go a short distance in a really long time. So imagine a snail. It's going to go 1 centimetre. It's going to take ages and ages to get there. So you need the longest time to go a very short distance, and that's going to give you the. Have to think of a real example, and that will help you. So once we've got that, we need the upper bound for the average speed. So what we need is the greatest possible distance. The biggest possible distance will be the upper bound for this value, 585, divided by the lower bound for this value, 15 seconds to the nearest second. So we go one below, half a unit below, so 14.5, and we divide those. So Daniela, you're thinking of 585. Well, let's have a look. So if we put those values in, 585, which is the upper bound for the distance, divided by 14.5, which is the lower bound for the speed, we get 40.34 meters per second. So that's the fastest that this car could possibly be traveling. How about the slowest that this car could possibly be traveling? So for this one, we do it the other way around. We need to take away the shortest possible distance and divide that by the greatest possible time. So now we're going the shorter value. And I know there's only tiny amounts in it, but if you were an engineer and you're working with a train, you'd have to be really, really accurate. So you need to be aware, especially when you're introducing lots and lots and lots of measurements, of this kind of error building up and building up, the more numbers you include. So we need to be very accurate. So the lower bound, let's see, even if it's just half a second, you have to be really accurate if you're working in engineering. Cause a train, that it will just really add up. So all these bridges that start going wrong, often it's because these error intervals haven't been taken into account. So what's the lower bound for the speed? What's the lowest that this speed can be if we rounded to the nearest 10 meters? Half of 10 meters is 5 meters, so we work out 580, take away 5, which is 575. You will get there. This is higher tier now, so we do have to think a little bit more carefully. So the lower bound for this distance is 575. Remember, 5 below, 5 above. And then we're going to divide by the greatest possible time. And the time is 15 seconds to the nearest second, so we need to go half a second above. 15.5 is the greatest possible time. So the numbers we're going to divide are 575 divided by 15.5, 37.10 meters per second. Now I've put that to 2 decimal places just so it's the same. Well, we were told in the question there to 2 decimal places. Okay, so the error interval for the speed of this car, so if the speed of the car was c, I don't want to put s because when I write an s it always looks like a 5. So if we put the speed of the car there, the lowest possible value to 2 decimal places is 37.10. So the speed of the car is greater than or equal to that. And it's less than 40.34. So the error interval, the range of possible values, given how it's been rounded for this particular question, is that the speed of the car, c, is between those 2 values. Okay, just have a quick look at the time. I know I started late, but 5 more minutes. Now, here is a summary of what we need to do. Now, when we're adding, it's quite straightforward. You get the biggest possible value by just adding the upper bounds of the 2 measurements that we're given. The least value, we just take the lower 2 values of the measurements that we've been given. That's adding, that's quite easy. If you're subtracting and you want to find the greatest value, you'll need to do the upper bound, subtract the lower bound. And if you want to find the least value, you need to do the lower bound of the first measurement, take away the upper bound of the second measurement. Multiplying, quite straightforward, it works just like adding. To find the greatest value, you just multiply the upper bounds of the 2 measurements. To find the least value, the lower bounds of the 2 measurements. And dividing similarly to subtracting works the other way around. So the biggest possible value divided by the lowest possible value. But rather than memorizing this, just be aware that you need to be careful when you're subtracting and dividing and think of it closely in the context of the problem. But the problems could be anything. They can be quite straightforward, they could be quite tricky. I'm going to show you very quickly before I go a question. This is from the same set of sample materials from Edexcel for the new 9-to-1 exam that I gave you a link to a moment ago. If you want a written solution, this is from the second higher tier paper, paper 2H, which is also a non-calculator paper. Here's a link to that question paper again. So this is from Edexcel's specimen papers. That's a link to the original document with all of the 6 sets of sample papers in it, and that's a link to the written solutions for paper 2H, non-calculator paper. So let's have a look at this question. If you're watching the recording and you want to pause it and have a go, please do so. Now the first thing you should say to yourself is, right, this is a right angle triangle, and I don't have any angles in it, so Pythagoras' theorem is probably going to come up here at some point. And we also have some measurements. We're told that A is 8.3 centimeters, corrected the nearest millimeter. Be careful because this is centimeters and this is millimeters. So what I would probably do in this case is write those measurements as millimeters, because then it's easier to take half a millimeter above and half a millimeter below to find the upper and lower bounds. I'm not sure, so yes, convert it into millimeters. So whenever you see a question that involves mixed units, stick to 1 unit. So either do everything in centimeters or do everything in millimeters, but don't mix them up. And then we're told that the length of B, so this is side A, that's the hypotenuse, the longest side opposite the right angle. And then we're told that the length of side B is 61 centimeters, corrected the nearest millimeter. So that's side B there. Now, I would probably just put these measurements directly onto the diagram. So you've got a big space that you're working out, but I think it's always much easier when you have a diagram in the exam to actually write the information on the diagram. And the examiner will see that and will give you credit for it. It doesn't matter if it can be anywhere, as long as your final answer, well, I mean, even if your final answer isn't on the answer line, as long as the examiner can see it clearly, that's fine. Now we want to calculate the upper bound for C, which is this length here. So what's the biggest possible value that this length here can have, and you have to show your working. Remember with these questions, so this is worth 4 marks. There's quite a lot of steps involved, but you need to get a strategy. The first thing I'm going to do is write down the lengths of the sides on the diagram and convert them to centimetres. That's easy, I can do that. Don't know if that's worth any marks, but it's a good start. So let's put that in. So the length of A is 83 centimetres, which is 83 millimetres. Okay. And I know that this question is going to involve finding the upper and the lower bound. So let's write those in while we're here. What is the lower bound for 83 millimetres? We've rounded to the nearest millimetre, so we need to go 0.5 millimetre below to get the lower bound, and 0.5 millimetre above to get the upper bound. So let's write those in while we're here. So the lower bound, the lowest value that this 83 millimetres could possibly be, 83.5, yes, that's the upper bound. What's the lower bound? So for the lower bound, you need to subtract 0.5. Perfect, Daniela, good. So the lowest value that the length of this side could be is 82.5 millimetres, and the biggest value is 83.5. Okay, so we've got that down. If you want to say that this is the arrows will imply that that's the upper bound and that's the lower bound. And then how about this length B? That's 6.1 centimetres. Convert it to millimetres. So in millimetres, 61 millimetres. And then again, we want the upper and the lower bound. So we want to take 0.5 millimetre off for the lower bound and add on 0.5 millimetres for the upper bound. So the lower bound will be 60.5. Perfect, Daniela. 61.5, sorry. Yeah, sorry, 60.5 for the lower bound. You're doing it the other way around. And then the upper bound, 61.5. Okay. So we've got our numbers. We need to put it into an equation. So we'd probably get a mark for those. I haven't looked at the mark scheme, so I don't know how they've allocated the marks. But do look at the mark schemes, because you'll get a lot of information about how the marks are allocated. So supposing you worked out the upper and lower bounds of those lengths, but then you had a complete mental block and you had completely forgotten about Pythagoras' theorem, you would get some marks for writing these in. Okay, so the next step is recognizing that it's Pythagoras' theorem, and that the length of the hypotenuse, actually, remember that I think I've done this slightly the wrong way around. So actually what we want is, no, that's right. So in this case, the hypotenuse is A. So A squared, the length of the hypotenuse, is equal to the squares of the length of the shortest two sides, B squared plus C squared. If I rearrange that, because I'm trying to find C, I take away the B squared from both sides. So remember, when you're finding the length of the shorter side, it will always involve subtraction. So make sure that you've got a subtract sign in there. So when it's Pythagoras and you're finding the length of the hypotenuse, it will involve adding. When it's Pythagoras and you find the length of one of the shorter sides, it will involve subtracting. So that comes from rearranging that formula. So write down the formula. Then let's put the numbers in. What numbers are we going to put in? Now, we want C, we're only interested in the upper bound. We want C to be as big as possible. So because we're subtracting, we're going to make this A value as big as possible. So we're going to use the upper bound for A. And the number we're subtracting to make C as big as possible has to be as small as possible. Yes, so upper bound to subtract lower bound. So this number here, B, we want to use the lower bound. Just checking the time because our office closes at 7 and I don't want to be locked in, which could happen, lower bound. So I'm just going to go through this very quickly so I don't get locked into the office. I started late. So there's our values. So we've put in the upper bound, subtract the lower bound, and these are all squared because it's Pythagoras' theorem, and the rest is quite easy. So once you've figured that out, you just work through the numbers. You've got your calculator. This is a calculator paper. So put the numbers in. Work them out with your calculator. Remember that's C squared. So to find the value of C, you need to square root both sides. Yep, 3312. So to find the value of C, square root both sides. So the square root of 3312 is this long number here. It doesn't say what we have to round the number to, so as many digits as you want to go to will give us our upper bound for the answer. And that's it. You want some more practice questions? Of course you do. Maths Genie is really good. So for all of these topics that I'll be doing in Unit 4, you want all of the practice questions towards the end of the paper, all of the grade 6 and 7. So grade 6, we've got here right at the top, rounding decimals to fractions. And then grade 7, we've got bounds. We'll do thirds next lesson. Here's some links. Now, each of these has got a revision video, which is fantastic. Hegarty Maths, I couldn't find any examples for this. So first of all, this is Maths Genie, so please do use this resource, even if you don't work through the questions in the textbook. These are all exam-style questions with solutions. So there's Maths Genie for you. I haven't heard anyone outside. I just hope I don't want to get locked into the office overnight. These are the revision videos and the questions and the answers for the rounding decimals. So have a go at those. And then we've got this grade 7 bounds. It's kind of tricky. So if you're aiming for a grade 7, this is one of the topics you really want to be quite good at. It will take a little bit of practice. The upper and lower bounds themselves are not too bad. It's the whole thing when you put it in a calculation, it can get quite complicated. So there's some practice questions. The revision videos. So if you go to Maths Genie and use any of these revision videos, they're very useful as well. If you bought Maths Buster for higher tier, error intervals and bounds is topic 5 there. So we're really getting into grade 7 stuff here. And then the recurring decimals is in this section here. That's really getting into grade 8 and 9 territory. Next lesson. We're going to be doing fractional indices and thirds. Thirds are a type of irrational number. They're quite good fun. To go on and do A-level, you'll be revisiting a lot of this when you go on and do your A-level maths. So that's it from me for today. If you have any questions, let me know. So I wouldn't say they're easy, but once you get your head around them, they're actually fine. So you'll be doing thirds. Oh, I'm not going to get locked in. I think the last person here goes at 7, so I've got 10 minutes. So hopefully I won't get locked into the office overnight. It's my worst nightmare. At least I get to work nice and easy in the morning. I just sleep under my desk or something, but my kids might be wondering where Mum is. So there's all of my contact details as always. If you have any problems or any questions that you want help with, let me know, or contact your tutor. And you can also use the forums. So have a look on the forums, and I'm happy to answer any questions on there. That's it from me for today. Enjoy the rest of your evening, and I will see you for tomorrow's webinar. I'll make sure I get the right link. I'll double check it 3 times before I post it on the site. So hopefully I'll see you at the normal lunchtime slot at 1 o'clock tomorrow for thirds. I'll see you then. Bye-bye. No worries. Bye-bye.